All right, kiddos, let's jump right into our second video for biochem. We're going to talk a little bit about solutions, and really, I'm not going to go really in depth into most of this stuff because a lot of this stuff are things that you should have had from Chemistry 1. I know that for some of you all that was a long time ago, or maybe you didn't have an amazing teacher, including maybe if you had me, I don't know. So when I gloss over some of this stuff, you can either read up some more on it in your text, or if you just ask me in class, I can sort of point you to the right direction of where we covered that stuff in Chem 1, or in a couple of cases where we might have sort of gone a little bit more depth in AP Chem. And you can sort of watch those videos maybe to help catch you up if we don't do some extra work in class, which we probably will for a couple of those topics. So mainly we're going to talk about water and about how water is pretty weird. And that's pretty important to us because when we're talking about biochemistry, most of what we're talking about are obviously chemical reactions that are going on in living organisms, which means that they're in aqueous systems, and so they're within that water. So first off, the thing that really makes water really unique is that water is polar, and it's not just a little polar, it's very polar. And if you remember, what that leads us to is something called hydrogen bonding. And so hydrogen bonding means that since the oxygen end of the molecule has a slightly negative charge and the hydrogen ends have slightly positive charges, that we're going to get some intermolecular forces, some intermolecular attraction that are essentially going to hold those molecules together. And you see that they align themselves so that the hydrogen end of one water molecule is facing the oxygen end of a different molecule. And this is obviously going to go on and on for the trillions upon trillions of water molecules that are in even a really small sample. This is going to give water some really weird, funky, unique characteristics. And so this polarity and these really strong hydrogen bonds are what lead to the really high melting point and boiling point of water. Generally speaking, boiling point and melting point have a lot to do with molecular mass or molar mass. And if we compared water to some molecules that are really close to it in molar mass, like say ammonia, some of those other things are actually going to be gas phase. So like ammonia, methane, those things are going to be in gas phase, but water's not. And in fact, water not only is not a gas phase at room temperature, but you have to raise it way up to 100 degrees Celsius before it boils. That's because those hydrogen bonds are holding those molecules together. They don't want to let go of each other. It's going to lead to high surface tension. So when you see, those little beetles skittering along the surface, that's because that top layer of water, those molecules are holding on tight to each other, so they can actually support a pretty good amount of mass on top of them. Things like capillary action, the fact that water is going to sort of climb up a really thin tube. Water's got a really high dielectric constant, which plays a big role into the solubility of substances. And so all of these things have a lot to do with the fact that water is a really unique molecule. It's bent, it's extremely polar, and that polarity leads to some really strong hydrogen bonds. So what does that mean for us in biochemistry? Well, the first thing is that it means that things that are ionic or polar are going to dissolve really easily in water. You probably remember the rule from Chem 1 that says like dissolves like, and that's a good rule of thumb in general. So something that's ionic, like say this sodium chloride crystalline structure, it's going to get dissolved by water because the positive charges, the sodiums, are going to get attacked by the negative ends, the oxygen ends of the water, and they're basically going to surround it and sort of pull it off the crystal. And then the same thing is going to happen to the negative chlorides, except that it's going to be the hydrogen ends that are positively charged that are going to surround it and pull it off. Okay, and what we would generally say then is the substances like this, and it's not just ionic compounds, it could be any sort of polar compound. What we would generally describe them as is hydrophilic. Okay, they like water, they dissolve really readily in water. They're not turning away from water, they're actively going to the water, and the water is enveloping them and essentially dissolving them. That is in opposition to hydrophobic substances. Now, hydrophobic substances typically means that those things that are non-polar, and you've got great examples of this. I mean, if you say tried to just put some vegetable oil in some water and shake it up, it's not going to dissolve, and that's because vegetable oil is a non-polar substance. It's actually a lipid that we'll talk about later in the year. And so since it's non-polar, it doesn't want to interact with the water. So instead what happens is you can sort of see it like if you shook it up pretty vigorously and looked in there, you would see like these big sort of clumps of the oil, and they would essentially be surrounded, and the water has to rearrange those hydrogen bonds in that structure that it sort of surrounds these hydrophobic things. This has some pretty big implications for us in biology and biochem. So the water molecules are going to rearrange their hydrogen bonding. They're going to form basically a little cage around it called a clathrate. And what does this mean for us in biochemistry? Well, probably the biggest example of how hydrophilic and hydrophobic are really so important to us in biochem is just something as simple as a cell membrane. A cell membrane is largely made up of things called phospholipids. And phospholipids are really cool because at one end of them, they have a polar end, okay, where the phosphate is down here. And then the other end is usually even actually a much longer chain even than this. But the other end is basically what we call an aliphatic chain, and you recognize this from organic chem, that this is essentially just an alkane chain, and sometimes alkenes, depending on what the lipids are. But this whole end here, the tails down here are nonpolar, and the heads are polar. And so what that means is that the heads, like water, okay, they're hydrophilic, so they'll go towards the water, and then the tails avoid water, and so they'll do whatever they can to avoid the water. So that leads to some really interesting structures. We get micelles here, where you see all of the tails are sort of inverted, and so the only thing that would be exposed to the water would be the heads on the outside. You can see a liposome forming in the same way, except that it's a bilayer instead of a monolayer. And then, of course, your typical cell membrane, essentially at its very basic, is a bilayer of these phospholipids, where you've got the heads facing out towards the fluid, towards the aqueous water, towards the aqueous solutions that are mostly made of water. And then, of course, the tails are facing in towards each other because they're hydrophobic. They want to stay away from the water. This, of course, the fact that a phospholipid can do both of these things gives it a special name, and we call them amphiphilic or amphipathic molecules. And that just means that they have a polar and a nonpolar group, and so part of them might like the water and then the other end does not. And soap is another great example. This is the reason that we use soap. Water on its own wouldn't dissolve grease because grease is nonpolar. But if you use something like soap, soap essentially has a polar end and a nonpolar end. So the polar end allows it to dissolve in water so that you can actually use it in the water, but the nonpolar end will actually help to dissolve the nonpolar grease, so that you can then get that, say, off of your dishes or off of yourself if you're washing yourself. And so those amphipathic molecules are pretty important to us in multiple ways, but of course cell membranes, pretty important. So a couple other quick hit things, and these things, again, I'm not really going to go into detail with. I'm not going to do the math behind them for you here, but what you can do is look these things up in other places, in some of my videos even, and pull those things down, or look them up in videos, or if you want to come in, outside of school and ask me some questions, we can do that as well. So colligative properties means that if we add something to a solvent, if we add a solute to a solvent, that colligative properties are those things that it doesn't really matter what the solute and the solvent are that much, but what matters is how many particles do we get in that substance. And so this has some pretty big effects for us. One of the biggest ones for us recently is freezing point depression. So the reason that we put salt out there in the roads is because that then is going to lower the freezing point of that water, and so it's going to help to essentially all of those maybe snow crystals that are around. It's going to make it so that they're not frozen in the solid state, that they're going to go into liquid state until a much lower temperature is reached. Now, depending on what the temperature gets to, if the temperature gets down to, say, -20, then that doesn't do any good. And so that's why in a lot of places, like, say, Alaska, they're not going to salt their roads very much to treat their roads. Instead, they'll put some stuff like gravel down, and then they'll put chains on their tires and stuff like that. But you can lower the freezing point of water in that way. And similarly, you can raise the boiling point of water by adding salt and other substances to it. Where this is going to matter to us most in biochemistry and biology is that osmotic pressure is also a colligative property. You probably remember osmosis. Osmosis, we said, is basically something self-diffusing through a semi-permeable membrane, i.e. the cell membrane, right? Phospholipid bilayer that we just talked about. And the way osmotic pressure essentially works is that if we've got a solution on one side of the membrane that has a lot of particles and a solution on the other side that doesn't have as many particles, the water is going to move through the membrane to essentially try to dilute the side that has the most particles, okay, so that they even out. And why this is pretty cool is like if we had water in a U-shaped tube, well, ordinarily it's going to be even on both ends, right? But if you've got that semi-permeable membrane in the middle, like a dialysis membrane, say, and you had more particles on one side, you wouldn't have to have the water at two even levels. They would actually split up a little bit because of that, because the water is flowing through to try to even out that concentration there. So osmotic pressure is going to be real important to us, and the fact that we have to worry about what the concentrations are matters a lot. This is why it matters what, say, the concentration of potassium ions in your bloodstream is, partially because of that osmotic pressure. Now, to go back into that, and we'll get back to the idea of the keeping the concentrations steady here pretty quick. Water is going to ionize itself to a really small degree. That allows us to get an equilibrium constant here. And if you don't know what an equilibrium constant is, that's okay. You can look up some of those AP Chem videos. And by the way, that colligative properties in the last slide, if you go to the Chem 1 videos, that's video 10.4. And you can look up AP Chem videos for equilibrium constants and for buffers that we're going to do here in a second to help you out with those. But essentially, water is going to self-ionize itself, and that means that if you take its equilibrium constant for water, okay, K is the equilibrium constant, W for water, the molarity of the hydrogen ions times the molarity of the hydroxide ions, and obviously if you put those two things together, H2O, right, are going to equal 1 times 10 to the negative 14th. And so that means that in a neutral sample of water, my hydrogen ion concentration should be about 1 times 10 to the 7th. So 0.3 or 6 zeros and then a 1. So a pretty small concentration on its own. And obviously that's going to change if we add acids or bases to it. If we know that hydrogen ion concentration, okay, that H plus concentration, we can then calculate pH. And you guys have been talking about pH like probably since elementary or middle school. But this is actually the math behind it. And again, if you want to go back and look at some of the Chem 1 stuff for that, I believe that one is probably a video 11.2 from Chem 1, and you can actually work through some of the math problems. That obviously is going to lead us to something called the pH scale. Now, when you look at this pH scale, you may immediately think like, wait a minute, when we talked about pH scale in middle school, we only went from like 0 to 14, and we were told there's nothing beyond that. That's actually not true. You can actually go below 0 on the pH scale. You can go above 14 if you get some what we call super bases. But it's not normal. Most of the time, depending on your concentration, okay, then you're going to be within a certain range. So if we've got a really high concentration of hydrogen ions, our pH is going to sort of go down here, okay? And so if we've got a really high concentration, we could actually go below 0. And so you see things like acids and tomato juice and vinegar, which is obviously acetic acid, down here on the low end of the pH scale. Neutral would be pure water, and that's because if we took an H plus of 1.0 times 10 to the 7th, plugged it in here, we would get 7 for our pH, okay? So it would be neutral water. Anything above 7 is going to be alkaline, and that's going to matter to us because things work out differently chemically if the solution is acidic or if it's basic. That has a lot to do with the chemistry of that particular situation. We'll talk a lot about a lot of those cases as we go into this stuff throughout the year. Now, living organisms don't want their pH level to change very much, and so we need these things called buffers. And buffers aren't just for living organisms. We can make them in the lab. We use them all the time. But they're really vital for living organisms. And so essentially a buffer is a solution that resists a change in pH. And the reason that it does that is because it's usually got some conjugate acids and conjugate bases in there that can essentially absorb some acids and bases when you put them in there. And two of the biggest ones that are important for us are the phosphate system and the bicarbonate system. The phosphate system is going to help to make sure that the intercellular fluid, the fluid inside of the cells, intracellular fluid, sorry guys, I think I mispronounced that, that fluid keeps its pH constant, because if that pH goes wrong, then all those organelles are going to die pretty quickly. And then the bicarbonate system is also going to regulate the pH of your blood plasma. That has to operate in a really tight range. And if that pH changes very much, then the cells and the tissues pretty much are going to die really quickly. And so those two systems in particular are really important to us. And again, if you want some more information on that, go look up some of those AP Chemistry buffer videos. And we'll talk in those videos a little bit about the systems. But And then if you're really interested in the math, you'll see that stuff there as well. The math of it doesn't matter to us really that much at this level of biochem, but in college you'll definitely be working out some buffer and equilibrium problems. All right, guys, thanks a lot.